Hi everyone, I'm Arifa Kokab and welcome to my capstone project called the Vocal Biomarker Estimate for Parkinson's Disease. My goal is to use voice as a low-cost, accessible signal to screen for Parkinson's disease and to monitor severity progression over time. Let's first talk about what Parkinson's disease even is. So, it's a progressive neurodegenerative disease that primarily disrupts movement. Think tremor, slowness, stiffness, and balance. But Parkinson's disease also has significant non motor symptoms like sleep and mood changes, cognitive shifts, and importantly for this project, speech and voice changes. Now, biologically, this disease involves a loss of dopamine producing neurons in a midbrain region called the substantia nigra, which throws off the basal ganglia circuits that help coordinate smooth movement. Now, clinically, diagnosis is based on examination and severity is commonly tracked with something called the Unified Parkinson's Disease Rating Scale, also known as UPDRS, which includes a motor section used in my work. Now, treatment like levodopa or deep brain stimulation can improve symptoms, but Parkinson's disease still progresses, so tracking changes between visits is important. And this is where voice is compelling. Now, Parkinson's disease often reduces loudness, flattens pitch, and increases breathiness or instability. Those patterns can be quantified from short recordings and used for screening and ongoing monitoring. And that's exactly the motivation behind the two models I'll show you today. Now, access to early screening and longitudinal follow up is uneven. My end users are number one, the public, who can get a quick screening signal, and number two, clinicians and patients who can monitor severity remotely. I use the Oxford Parkinson's Disease Voice Dataset for screening and the UCL telemonitoring dataset with clinician rated UPDRS scores for progression. I extract acoustic features from short sustained phonations using parcel mouth, and the deployed app does not store audio, it processes in memory only. Now, before I list specific metrics, I want to define features. Now, think of features as numbers I compute from the sound, like the average pitch, how steady the pitch is from cycle to cycle, how steady the loudness is, and how much harmonic energy there is versus noise. Now, instead of pushing the raw waveform into a model, I convert each short recording into a compact table of statistics. That makes it easier to learn patterns, compare different visits, and reduce sensitivity to microphone or rooms. Now, why do these numbers help us with Parkinson's disease? Well, biologically, Parkinson's disease can reduce breath support and make the laryngeal muscles less precise. Now, clinically, this shows up as hypophonia, which means lower loudness, monotone pitch, and a bit more instability in the voice. Acoustically, that often looks like higher jitter and shimmer, which sort of means less steady pitch and loudness, and lower HNR, which means more breathiness or noise. Now, those changes can be picked up earlier than big changes in clinic scores, which is why voice is a good fit for screening and ongoing monitoring. Now, the important part is that the same feature pipeline feeds both of my models, the random forest for healthy versus PD screening and the BiGRU plus 1D CNN that tracks changes in motor UPDRS scores in between visits. I extract features from a short sustained using Pratt via parcel mouth. Now, first is pitch, the fundamental frequency F0 and its range, average, highest, and lowest values over the sample. Next is jitter, which quantifies tiny beat to beat changes in pitch. I use standard measures like REP, PPQ, and DDP. Now, shimmer is the twin of jitter but for loudness, cycle to cycle amplitude changes, and I use APQ3, APQ5, overall APQ, and DDA. I also look at the ratio of harmonics to noise, which is HNR, and its inverse, NHR, which gives a handle on breathiness or hoarseness. Now, beyond these, I include compact nonlinear summaries like DFA, which basically tells us how fluctuation persists over time, D2, which is signal complexity, spread 1, spread 2, which are like the spectral spread, and PPE, which means pitch period entropy. Now, for clinic relevance, if there are several phonations recorded in one session, I average them at visit level so the label, UPDRS score, and the features line up. Now, these particular features are well studied in Parkinson's disease speech. People with Parkinson's disease often show higher jitter shimmer and lower HNR, plus changes in the pitch behavior, patterns that my screening and progression models can learn from. Let's begin with the screening model for Parkinson's disease. This model is a fast screening check. The flow is simple. At home, I ask the user to hold an ah sound for about 5 to 8 seconds. The browser sends that to the backend where I convert it to mono 16 kilohertz wave format, extract a compact set of parcel mouth features, things like pitch steadiness, loudness steadiness, and harmonic to noise, and then run a random forest. The output is a probability plus a plain language label like either likely healthy or likely PD or Parkinson's disease. Now, if the result is concerning, the guidance is clear. Follow up with the clinician. Now, quality and privacy are built in this. The app prompts a re record if the audio is too short or noisy, and all processing happens in memory, so no audio is stored. The public demo is available via the CarePath AI Foundation website. I trained this classifier model on the Oxford PD Voice dataset of 22 engineered acoustic features with the binary status label with repeated recordings per patient. I then made a feature correlation matrix. Now, this heat map shows structure among acoustic features. Jitter and shimmer families cluster tightly, while HNR and HR trend in the opposite direction. Now, that pattern supports a non-linear model like random forest and reminds me to be careful when interpreting feature importance because many predictors are correlated. Let's delve deeper into the screening model. Since each person contributes multiple recordings, I split the data with group k-fold by patient so the model never sees the same speaker in both train and validation. I also keep a grouped holdout for the final check. Now, the classes are a bit imbalanced towards PD, so I use class weight balanced and keep folds stratified. For the classifier, I chose random forest. I ran a small grid over tree count, depth, leaf size, and maximum features, and the best trade-off was 500 trees, SQRT, 2 leaves, and a constrained depth. At inference, I don't use the default zero point 0.5. I picked an operating threshold from the ROC to favor sensitivity for screening and fixed it at around 0.63 in the public demo. The image on the slide is basically a general idea of how a random forest model works. So many trees vote, and the final probability crosses the chosen threshold to produce the likely healthy or likely Parkinson's disease label. The classifier leans most on MDVP, APQ, Shimmer APQS, and Jitter DDP, which aligns with dysphonia literature. F0 related features follow. Seeing stable importance across folds gave me confidence the model will generalize to typical browser recordings when the signal quality is reasonable. The AUC is around 0.97. Now, in the public app, I do use a fixed threshold designed to favor sensitivity while keeping reasonable specificity. The app clearly states that it's a screening tool and not a diagnostic, and the goal is to nudge someone to follow up with a clinician. For deployment, I keep it simple and portable. The front end is a combination of React and Vite, which was made with JavaScript. The back end is a Flask API made with Python, served by Gunicorn on Render. My trained random forest and the exact pre-processing steps ship together as a single RF underscore model PKL, so inference matches training byte for byte. Here's the flow. The browser records a short ah. The API converts it to mono 16 kilohertz using PyDub, which then extracts the parcel mouth features, which runs the random forest, and then returns a probability plus a clear label. Audio is processed in memory and never stored. So if the clip is too short or too quiet, it returns a friendly re record prompt rather than a shaky prediction. Configuration is minimal. The front end's API base URL is set via environmental variable. CORS is restricted to the site's origin, and HTTPS is handled by the host. Operationally, I monitor request latency and error rates, and I keep a light drift check using population stability index over the feature distributions. So if drift grows or calibration slips, I refresh the threshold or retrain. This gives me a reliable, privacy-preserving demo that's easy to maintain. Here is the CarePath AI Foundation website where the classifier model for screening for Parkinson's disease via voice has been deployed. Now I will click on start recording and I will record myself saying ah for 5 to 8 seconds. So let's go ahead and do that. Ah. And then you can hear back what you recorded here, and then you will just basically go ahead and click run analysis. And it says likely Parkinson's disease. And ideally, this is better for people who are aged 50 and above. Let's now move on to the second model, which is to predict severity progression for Parkinson's disease. This model is to support patients that are undergoing treatment for Parkinson's disease. Now, in between visits, I want this to work like a check engine light for voice. Now, the flow is simple, like before. At home, the patient records a short ah, and the app extracts features like pitch, steadiness, and noise, and the progression model estimates the next absolute motor UPDRS level, not just the direction of change. That's important because visit to visit changes are usually tiny and noisy. However, the absolute level stays well calibrated, so it's reliable for monitoring. To avoid alarm fatigue, I use conservative thresholds. If a single visit shifts by zero point 0.5 or more, I flag it. If the 3 visit rolling sum reaches 3, I flag that too. The user interface keeps it simple. Green means stable, keep routine. Yellow means mild drift, recheck soon, and note contexts like sleep or meds. And red means a notable change, which means message the clinic or move up telecheck. Over time, patients and clinicians can see trends that line up with medication timing, illness, or stress. Once again, this is not a diagnostic device. It is an early warning and triage tool. Audio, again, is processed in memory, not stored, and the app asks for a re-record if the sample is too short or noisy. The goal is simple. Surface meaningful changes earlier so care can happen sooner and not months later. For monitoring, I predict the next visit change in motor UPDRS. The distribution of delta UPDRS, which means the change in UPDRS, is narrow and centered at 0, so predicting the sign at short horizons is hard. I optimize for a calibrated absolute level and trigger alerts using conservative thresholds, zero point 0.5 per visit and 3 cumulative over 3 visits. UPDRS levels show strong autocorrelation that decays with lag, so deltas are only weakly persistent. That motivates a BiGRU for longer context and a 1D CNN for local motives. So the model captures both slow drifts and short transients in the speech derived features. This model focuses on monitoring, not diagnosis. I predict the change in motor UPDRS to the next visit and then add it to the last score to reconstruct the next absolute level. I first aggregate multiple phonations into one visit level row, then normalize per subject so each patient's baseline is removed. I feed short 5 visit sequences into a lightweight BiGRU and 1D CNN structure. The recurrent branch tracks trend, while the convolutional branch picks up local blips. I combine them and use a small linear head. Training uses Atom with the learning rate scheduling, dropout and L2 for regularization, and mixed precision for stability and speed. To avoid leakage, I split by subject with group K fold and keep a subject held out test. In the app, I turn the predictions into conservative alerts, flag a single visit jump of zero point 0.5 or a 3 visit rolling change of 3, useful for triage between clinic visits. The severity progression model showed interesting performance. Now, I'm showing two diagnostics here. On the left is the calibration scatter plot. Now, this plot shows the predicted score versus the true motor UPDRS score. If the model is well calibrated, points line up along the 45-degree line, and the slope tells me how close I am to perfect calibration. And the R square score shows goodness of fit on the absolute scale. Now, from this calibration scatter plot, the slope is about 1.01 with an R square score of about 0.996, and the intercept is small. Visually, the points hug the diagonal, which means my absolute severity estimates are very well calibrated. That's exactly what I need for threshold-based early warnings. Now, on the right, you'll see the Bland-Altman plot. It graphs the difference, which is the prediction minus truth, against the mean of the two. Now, this is used in clinical measurement to detect systematic bias and to quantify limits of agreement, like how far off I am, typically across the score range. Now, from this Bland-Altman plot, the average bias is about negative 0.19, and the limits of agreement are roughly negative 1.15 and 0.77. So, across the clinically relevant range, errors cluster within about a plus minus 1 point with no strong trend across the x axis, so no obvious range dependent drift. On held out subjects, the MAE on absolute motor UPDRS is about 0.433. A naive last value baseline is about 0.427, and ridge regression is about 0.481. The delta direction accuracy is around 46.5%, which is expected because visit to visit changes are usually small and noisy. The key takeaway is that the level predictions are calibrated. So when the model signals a jump of greater than or equal to zero point 0.5 in one visit or greater than or equal to 3 over 3 visits, that's a meaningful early warning sign for triage. I want to be explicit about the scope of this project. This system is for screening and monitoring, not diagnosis. Any concerning result should route to a clinician, and the model should live in the loop, not replace judgment. On privacy, I designed the screener so audio is processed in memory and not stored. Transport is over HTTPS, and the API keeps minimal metadata. If I later collect real patient audio, I will do it only with informed consent under an approved IRB protocol and in alignment with institution privacy policies. Now, the datasets used here are modest and not fully representative. They can be skewed by age, sex, accent, and language. that creates fairness risk. My mitigation plan is to evaluate performance by subgroup, recruit a more diverse cohort, and recalibrate as the data broadens. Real world audio is messy, so different microphones, rooms, and phones shift feature distributions. I plan device calibration checks, population stability, monitoring on features, and periodic threshold refreshes to handle drift. UPDRS score labels are rater dependent and noisy, so I emphasize calibration and trend detection over crisp direction calls. Firstly, I try to manage human factors. I prompt for re record on low quality clips, show plain language confidence, and include clear next steps so the tool informs action without creating alarm fatigue. In summary, I delivered a full voice biomarker pipeline with two complementary models, a quick screening classifier and a progression severity predictor for between visit monitoring. I showed feasibility end to end, record, extract, infer, display with a lightweight privacy preserving app. The value is practical, early warnings, and simple trends that help patients and clinicians act sooner, not months later, for Parkinson's disease. To close, here's how I'll move from a solid prototype to something more useful in practice. Now, in terms of product, I'll ship lightweight dashboards for clinicians and patients so trends are easy to read at a glance. Now, thresholds will be configurable per clinic, and I'll let users add simple context notes like sleep quality or medication timing so odd readings have an explanation. Now, in terms of data, I'll expand the cohort to be more diverse across age, sex, accent, and devices. And I'll standardize captures so microphone and room effects are controlled. For any new real world audio, I'll submit to IRAs and collect only with informed consent. Now, in terms of modeling, I'll add some modern voice embeddings alongside the engineered features that refine the BiGRU and 1D CNN so it stays compact and stable. I'll also add uncertainty estimates so alerts carry confidence and can be tuned for risk tolerance. Now, in terms of governance, for any patient partnerships, I'll align to HIPAA and sign a BAA. I'll publish a CPRA aware privacy policy, meet WCAG accessibility, and set up drift monitoring, PSI on features, with a scheduled threshold calibration review. Now, these steps turn the demo into a safe, maintainable tool that supports screening and between visit care without overstepping into diagnosis. Thank you so much for your time and have a nice day.